But I probably won't be doing lead code before that because like if I
Yeah.
fail, it'll just make me nervous.
All right. It's recording. So I got three questions up. How are you feeling one day out from your interview?
Um, Feeling all right. Feeling a lot more nervous than I was before. Just because there's only one day left.
What are you feeling before your? Oh, you're just. Are you feeling prepared though?
I guess I just don't know what to expect to be honest. I don't know like what specific type of questions they might ask, so
Yeah.
I just really have to I guess like practice all of them.
Yeah. So today we got more practical questions. We're gonna start off with a sliding window. I just want to see that you have the implementation down, and we have two designing data structure type questions, which should be fun.
All right.
Yeah. But try to before your interview, don't maybe study a little bit before your interview, or maybe I don't even know. What I do usually is if I was already grinding a whole month before my interview, the day before my interview, I'm not gonna do anything. I'll do basic studying because I'm just trying to
Yeah,
take a
maybe.
rest day right before my interview, and then during on interview day, pretend my interview's at like 1. Maybe I'll wake up early and I'll look at a few notes, but then I won't just kind of warm up. Maybe do one or two questions in the morning.
Yeah.
Just quick warm up. But even ones that I already know, I just want to make sure that I'm typing fast and I'm like able to write non-buggy code real quick.
That makes sense, yeah.
Like small warm up. Like when you're playing, like if you play basketball, like right before the game, you gotta get some shots up. So,
Yeah.
so, so I don't
Makes
know.
sense.
Yeah, cool. Let's just hop straight into this because I know you got school. I'm gonna send you this invite. But dude, people are really think you're good. So on the, do you see the comments on the second video?
Second video, no.
People are like, I'm cooked, I'm cooked. Watching you. But I told them, I was like, you're actually pretty good, especially for a freshman. All right, let's get it. Start it up.
Okay. So max consecutive ones. So given a binary array nums and an integer k, return the maximum number of consecutive ones in the array if you can flip at most k zeros. Okay. So in the example one, they give example one they give on one. Actually, let me just copy it. They give that, and then the reason why the output is 6 is because if you look at zero, if you look at from the right, there is one, two, three, four, five, six. Since you have the leeway to transform two zeros into ones, which is k equals 2, then that's your maximum. Um, okay. And then I guess, like, as a human, like the human algorithm for me would be to, I guess, sort of, look at the first element. And if I see it's a 1, I'll be like, okay, I have k equals 2, so, maybe I could transform to a 0. And I look at the next element. I'm like, okay, I have the k equals 1 now. So that's two zeros. I'll just write that out. So we have k equals 2. So I might start the first element. And so I see that, okay, once I do that, then I have, whatever comes after, and now my k is equal to 1. And then the next step, I see that I have 0, and then, I can transfer the next one to 0 because it's a 1, right? 0, 1. But now the rest of the array is ahead of me, and I have k equals 2. So when I look at the next element, right, 0, 0, 1, and look whatever comes after, my k is going to be equal to 0. So I really can't continue. So at that point, I guess me as a human, what I would do is I would sort of, I guess, give up on the first 0, right? And sort of almost do like transform it back to a 1. Second, make the second one into a 0, and then make the third one into a 0, right? So now my k is going to be still equal to 0. Like now I have at least the whole rest of the array ahead of me. And then I see that, I have like zeros coming up. So once I ditch that first 0, or the first element, I see that I have 0, 0, 0, 0, 0, right? Which is 1, 2, 3, 4, 5 consecutive elements.
Mm-hmm.
and then the whole rest of the array is ahead of me. And now this is obviously not the largest one, but let me see if like you with this algorithm that I'm describing, can I get to like the actual answer? So
Well, we want ones, right? Or zeros.
yeah, we wait. Oh yeah, I'm going at this wrong. Okay, wait. Oops. Yeah, so it's the we want ones, yeah, not zeros. Um, wow, this entire thing is wrong then. Okay, so yeah, so we have one, and then the whole rest of the array ahead of us, right? So we see that k is still equal to two, right? Because we look at the first element, we look at the second element, they're both going to be one, and actually we look at the third element, just for that matter, right? Okay, and now we see that ahead of us is like a zero, and so we might say that our k is equal to one, right? That's the amount of leeway we have now for transforming ones into zeros. So one, one, one. We might pretend that the next element is a one, and the next element is a one, right? But that element was originally a zero.
Okay.
One, one, one. No, yeah, k is still equal to two here because we didn't transform anything. And now here k is equal to zero because we transformed these zeros into ones. Okay, and then when I reach my let's see, after this, there's going to be a zero right here. But our k is equal to zero, so we want the maximum number of consecutive ones, right? So at this point, what a human might do is, since we're looking for the maximum consecutive, well, we would probably have to store this consecutive, right? So far, I guess I can write max equals 3, max equals 3, max equals 5, max equals 5, right? I guess me as a human, what I would do is I would give up on that first element until my k is no longer 0, right? Because I have to transform this 0. So I would be like, I'll just indicate x to show that I'm not considering it anymore. So I have 1, 1, 1, 1, 0. And then I'd also have to not consider, basically, I'll just have to not consider all of these until I reach my first one that I flipped at the beginning here, right? Do you see that? The first one that I flipped, I'm going to turn that to x. And then now I sort of have the leeway. Okay, now I can say, okay, my k is equal to 0 now, finally.
Mm-hmm.
My max is still equal to 5, but the current one that I'm considering is 2. Okay, and I guess I'll just repeat that process again and again. And so let me see if using this process, I would reach the actual correct answer. Let's see, x, x, x.
I see.
All right, and then
I'm a
uh,
bit confused with the arrays. Like, are we making copies of arrays? Like, what's the algorithm here? Are we doing like a
oh
double for loop?
no, we're not going to be replacing actual elements within the array. When I say x, I just mean like we might have maybe two variables, like maybe L and R, which indicate uh, the range of values that we're considering.
Okay.
So if an element is marked x, then it's not within LR. Does that make sense?
Yeah. Okay.
Okay.
How are we capturing the max?
We so at any point, max is going to be equal to L minus R plus one. Hold up. L. So if this was our max, right? 1 minus 0. Yeah, L minus R plus 1. Max of that with max. I guess it shouldn't be called max. It's like maybe result. So at any given point, the maximum is going to be the maximum between, I guess, the range that we have and the current maximum.
Okay. So with this array, we're gonna have a left and right pointer. We're gonna move. What are we gonna do? Could you show it like this? We're gonna do.
Yeah, sure.
And with the other
So
variables, because creating
yeah,
the copies is a bit confusing. It's adding a bunch of extra lines.
yes. Sorry, I didn't mean to create copies. Like actual in the code, I didn't mean to create copies. But yeah, so starting from left and right, uh, we're going to initialize maybe. Let me see the constraint. Yeah, num's length is 1. Okay. Um, so yeah, so here we see that the actually we might have to start R at 1.
Okay.
And then if the length of the array is 1, then we can just maybe return.
Mm-hmm.
Um,
Store
Actually, no, that's
maps
not.
here.
Yeah. Okay, so when you see R and L, right, um, we see that. Um, okay, okay. Actually, okay, so we start both of them at the beginning. And then the one that we're going to be moving right now is R, right? So we see that the current element at R is 1, so that's fine, right? We don't have to do anything with K. We don't have to do anything with maximum.
Okay.
Actually, we do have something to do with maximum because right now maximum is going to be equal to 1 because we see that, what is it? R minus L, 0 minus 0 is 0, plus 1 is greater than 0. So right now our maximum is going to be 1.
Okay.
Okay. And then the next iteration, we're going to move R again. We're not going to move L for now. We're going to move R. And then we see that, this is still 1. So we don't have to do anything with K.
Okay.
But our R minus L is now going to be equal to 2.
Okay.
Right, isn't our K equal
I
to
just
2?
changed it to one right now for the example, just to make it simpler, because it's gonna yield the same result if it's one or two. But I just
Okay.
want to make sure that we could just like usually it's better to craft a smaller edge case, otherwise we
Okay.
might be here for too long.
Yeah.
Okay, there.
Okay. So yeah, we have R. And then, okay, we're just going to remove R over again. And so now here we see that, okay, our current element's 0. But that's theoretically fine, right? Because our
Hmm.
K is equal to 1.
Okay.
So we can sort of uh, we can sort of call this maybe current K, almost, and then we're given K in the parameter list.
Sure.
So our R is, I guess we only move L when current K is going when current K is probably equal to 0 and array R is equal to uh, 0. Let me see if that's right.
Sure.
So current K is 1, so we're going to subtract it and we're going to make it 0, right? And that's fine because we have that leeway to do so. Okay, so we're fine. We can keep moving R. But then here's when we have like a complication, right? Our current K is equal to 0, so we can't move R. So I guess I can write that here. We only move R when current K is greater than 0. Yeah, we only move R when current K is greater than 0. So here current K is equal to 0, and so we cannot transform it.
Mm-hmm.
So the only thing left for us to do is, in order to start exploring the rest of it, we have to start moving L until our K is no longer 0.
Okay.
So move L until current K no longer 0. Right? And the way you know that is, let's say we can move L up. Okay, is that a 0? Or we can start here. Okay, is 1 a 0? No. Okay, so we can't do anything with K. So we move up. Is 1 a 0? No, we can't do anything with K. So we move up, and we see, oh, okay, this is equal to 0. So what we can do is we can make current K back into 1. But then we also have to stop considering this, right? That's the trade-off. We can't consider that 0 anymore. So we can only start considering from this 0.
Mm-hmm.
Okay, and then you just sort of repeat that process, right? So now our K is equal to 0. So now we have the leeway to start, going L. Then we can go L over here, and then L over here. And the whole time through, I guess I didn't visualize this probably well enough, but the whole time through, we're going to see if, okay, is L minus R plus 1 greater than the current maximum, right? And then by doing that, you would arrive at the solution, which is 6, right? Because here we see that L minus R. Oh, wait.
But how come the
Uh,
L's moving forward past the R?
oh, yeah, sorry. I meant to move the R. Oops. Yeah, so we see the R. And then when we see the 0, we see that, okay, we have to flip current K back into 0. But we can do that, right? Because we can, yeah.
Okay.
So now we see here R minus L. Oops. R minus L plus 1, that is going to be equal to 6, which is greater than any other subsequence that you've encountered so far.
It's 6, but we only have K is equal to 1. We only want K equals to 1, right?
Oh, wait, yeah, this is an original example. So let's see. With this example, we have 1. I guess so R would never be here, right? Or R and L would never be in that position because we only have K is equal to 1. So at this point, we stop because current K is now equal to 0.
Mm-hmm. But k was already 0 before.
Wait, hold on. I think I messed myself. So, you said current k is equal to 1, right?
Yeah.
Okay.
Okay. It's just
Uh,
a smaller example.
yeah, yeah. So yeah, we would start from here and then we would end here. So yeah. So current k is 0 when at this point when r is right before the last element. So we'd see here that the current range is going to be 1, 2, 3, 4. So that's going to be 4. And then, like I said, since current k is equal to 0, we can't move r anymore. So what we have to do is we have to move L until the current element is no longer 0, which right here, that's what happens. So now we can make current k back into 1. And then we can sort of start moving r again.
Okay. Okay.
So now
Sounds
here we
good.
see that,
Let's
yeah.
implement.
All right. So uh, I guess I'll pretty much do exactly what I just said. I'll just do current k k can be 0 actually. So yeah, so current k can just be equal to k for now. And then and we can initialize L and R to both be 0 for now. That's fine. Um, and we see here that we sort of end our thing when R is at the end. So I guess we can say while R is less than while R is less than the length of what's the array called? Nums. We sort of have to do two things. We have to result. Let's say result is going to be equal to 0. Okay. So let's see. Let me look at my logic that I just pretty thoroughly described.
Mm-hmm.
We move L when current k is equal to 0, or let's move R first, right? Because R is the simpler one. So if current k is greater than 0, we can move R. And we can move R. I think before that, right, we have to, I guess, check the current element, right? If nums R is equal to 0, yeah, because that's something we have to flip. If nums R is equal to 0, then we say current k minus equal 1. Okay. Yeah. So how would that handle a current k of, like, let's say current k started with 0. I'll handle edge case later, but I'll say for now, to do handle k is equal to 0. Okay. So current k minus 1, and then if current k is greater than 0, then sort of, r plus equal to 1. Else, we have to sort of increment L plus equal to 1. Let me see. Sorry, I'm going to take 1 minute to sit in silence a little bit.
Sure. Yeah. Go
Because,
ahead.
okay.
But it says you're looking it up. I'm just kidding. By the way, they have markers and stuff. Like if you move out the browser, it's gonna tell them.
Yeah,
This one's
I'm not
crazy.
going to do that,
Yeah,
bro.
yeah. But just in general, they just added that feature. It's crazy.
Yeah, so we start at the beginning, L, R, current K, 0, R, 0. Yeah, else L plus equal to 1. The L, okay, so we move L when current K is equal to 0 and R is equal to 0. So if else, let's see, well, I might have like maybe a nested while loop here.
Mm-hmm.
There might be a better way to do this, but this is just the way I'm thinking about it right now. So while see while nums L is equal to 0, right? We're going to be doing L plus equal 1. And so by this point, we can be assured that nums L is no longer equal to 0. So we can say current K, we can sort of increment current K by 1, right? Because now we have the leeway to start flipping more zeros. Let me see if that makes
Yeah.
sense. So here if L started here, yeah,
Okay, we
yeah,
have
and
to
then
do
L,
a quick time check because I want to get through the other two questions.
yeah.
One,
Does it look like I'm on the right path
yeah,
for now?
no, you're definitely on the right path, but I think implementing it is going to be the problem, right? Because I think you're almost on the right path here, but the implementation is a bit crazy.
Yeah, I haven't done this in a long time.
Let me walk through it quickly because I could show you how to implement it very simply, and then let's move on to
Okay.
the next question because we want to focus on um, breadth over here over depth. Like I want you
Right.
to see multiple questions today.
Yeah.
Um, so k is equal to 1. We can do something like the num zeros we seen, right?
Hmm.
Because the moment we see two zeros, or the moment we see more zeros than we can flip,
Yeah.
where it doesn't work, right?
Yeah. So you have to
And
start shifting your window. You have to start incrementing L.
so the way I'd like to think about it is like we keep expanding our right pointer until we can't anymore, until it breaks the constraint.
Yeah, that's sort of what I tried to
Yeah,
do.
that
It's
is
pretty
you did
messy.
mention it, but what's it called? So what I would do here is we have our left and right.
Hmm.
I like to use spell it out. But what we'll do is pretty much like I just mentioned during pretty much we expand our right pointer until we can't anymore, right?
Yeah.
So what we'll do is we'll say if the nums at right is equal to 0, we increment our num zeros. So
Hmm.
like pretend let's look at our example up here, right? If it's equal to 0, we increment it. It's not, so we just move our right pointer, right?
Hmm.
And then we have you're right, we do a nested for loop. That's what I like to do as well. But what I say is while left is less than equal to right, or less than right, and the num zeros is greater than k. That means that we break the constraint. That
Yeah.
means we have to move over the right pointer, right?
Yeah.
We have to shrink it. But at the same time, what I'm doing is nums if we have another check here. If nums left is equal to 0, so if we see a 0, we retract it. But essentially, after
Yeah.
here, we just capture the result, which is max of result. And you're right, it's like right minus left, and it's either +1 or -1. Probably +1, right?
I think it's +1.
Yeah.
Yeah. Or couldn't left and right be at the same position? Right here?
Could left and right be at the same position?
Like in this while loop right here. Line 34.
But we want to break it when it's at the same position. Because then
Oh,
that's
right.
that's
Yeah.
when
Yeah.
it's
Yeah.
at the start.
Yeah.
That's when it's at the start, right?
Yeah. Makes sense. Oh, it didn't work.
While left. Wait, where's num zero? This 12, 6, 12 result. Right minus left. Let's see. So we increment.
Cause I think it's because
What?
you should do +1 right here.
Yeah. Shit. It's off by 1. Okay, just right minus left.
Oh, okay.
So that's kind of like the boilerplate to do it. Like expand it. She used like way less if conditions. You had a bunch in there.
Yeah, yeah. I was like overcomplicating it, I think.
Yeah. So just think about it like we expand it until our condition breaks.
Hmm.
and that condition is going to be different depending on the question. But usually you just want to copy the same boilerplate where you're expanding,
Yeah.
and then you just figure out when I can contract it. And that's usually you just update this line right here, and then you do some other bookkeeping. The other only bookkeeping we do right now is counting the zeros. So this one's easy, but some of them you're
Yeah.
doing way crazier bookkeeping
Yeah.
to
I was like over engineering it because I was like basically doing it from scratch.
yeah.
Okay, but yeah, now I know. Now I know.
Okay,
Okay.
cool.
Next
Yeah,
next question.
you got the good into. Oh, and okay, one thing would be, let's see. One thing I'd be what to say is like quickly clarify the question. Like ask
Hmm.
some things related to figuring out the constraints of the question. Like, is it just gonna be ones and zeros, right? If someone says max consecutive ones, like you automatically assume that zeros, but
I mean, in the well, it would work for another question, but in this question they say it's a binary array,
yeah, it's
so that
true.
would kind of be that would be a dumb question.
Yeah, yeah,
But I guess a good question would be can k be equal to one or can k be equal to zero, right? That'd be a good question if they didn't tell you the constraints.
yeah. Like honestly, in an interview, they wouldn't drop this whole thing, so I'll just make sure to do some clarifying questions of just the inputs.
I heard
Um,
they don't reveal every aspect of the question,
yeah,
just so you can ask questions. Is that true?
yeah, exactly. So, for example, there's some questions that are sliding. There's one that Facebook likes to ask where they're gonna be like, okay, can you find the longest subarray of size k? You might think it's sliding window, but if you clarify, if they say there's negative numbers or there's non-negative numbers, it's gonna change this optimal solution from a sliding window to a hash map. So if you don't clarify, you like automatically get to the wrong solution. So like this one, like I would just make sure to practice doing that, even if it, of course, like the whole question is gonna say it here on LeetCode,
Hmm.
but I can't because I can't delete it, any of the prompt here for you. But just try to clarify with me.
Yeah.
And yeah, this one is kind of harder, but yeah, that's one thing. And another thing would just be with the sliding windows. The way I like to do it is with the left and right pointers, like I did there, and actually show like what my variables are, or like moving the left and right pointers up,
Hmm.
because you were creating some copy, so I wasn't understanding what exactly you were trying to do there.
I see.
But yeah, how do you feel about the question?
I feel like I knew what to do from the start. I was just like implementing it like crazy
Mm.
because it's been a while since I implemented it. So I was like basically thinking about how do I do this algorithm from scratch. Whereas when I do DFS or like BFS, like I pretty much it's like second nature. But like this isn't. So I feel like that's where I got tripped up.
Okay, cool. Nice, yeah, good work. You were able to figure it out. Let's move on to this next question. Send it. I'm gonna send it in the.
Okay, min stack. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Okay. So yeah, in the stack, it supports all the stack elements or stack methods: push, pop, top, get, min. Okay. I have a question. Am I to assume that, like for example, am I to assume that maybe top and get min will be called on a non-empty stack, or should I implement some sort of error handling?
Yeah, good question. It will always be called on non-empty stacks.
Okay, and pop as well too, right?
Yeah.
Okay. Uh, okay. So so design a stack that supports push to pop top. Are there any space constraints for this question?
No.
Okay. There might be a better way to optimize space for now, but I think okay. Uh, well, I know that if I wanted to do pop and top, if I wanted to do pop and top in constant time, I think I would pretty much need to have a sort of nested stack,
One quick
right?
thing
And
would be another possible clarifying would be like, okay, what can we store in the stack? Is it just integers? Is it just strings? Is it can you push objects?
Oh, yeah,
Okay,
okay.
okay, but continue.
So, yeah, can we store non-integers in the stack as well, or is it just integers?
Just integers for this one.
Okay.
Yeah, because yeah, and then maybe another one would be like yeah, because it's important in this one because we're calculating the minimum element, right? So I'll
Yeah.
calculate what we exactly mean by that. When it but like integers, I mean it's obvious.
Yeah, and the problem says that negative integers are allowed. Okay.
Mm-hmm.
So because push, pop, and top need to have constant time, I'm thinking that I would probably have to have some sort of I guess stack in my question, right? Because stack is the only data structure off the top of my head, and maybe like a double-ended queue as well, if we were
Sure.
considering that.
Yeah.
Stack and double-ended queue are the only ones I would know off the top of my head that
Yeah.
can support getting push, pop, and top. So yeah,
Makes
maybe
sense.
nested stack or deck. And then, okay, the part of the problem that requires getting the minimum, I think to help me answer that question, I think I should go through maybe an example. Okay, so in example one, they push they push -2. So now our stack, like imagine, uh, I don't know how you'd visually represent a stack, but imagine the first element, imagine the last element is like what you would pop off. So push -2, uh, you'd push 0. So now, okay, when we push 0, we have to think. Uh, so now we would have, if we just used like a raw stack, it would be -2 and then 0. And if we pop that off, if we did get min, we want to get -2. When we do get min, we want to get -2, but when we get pop, we want to get 0. So let me write that out. Now when we do pop, it should get 0, but get min -2. Get min should return -2. So now the question that I have to answer for myself really is, okay, how if this was like a really big, let's say we had like tons of like garbage elements here, right? Getting the first element off the stack would be O of n, and then pop pushing that back onto the stack or whatever, that would just be like way more complicated than it needs to be. So we can't just rely on like one stack, or maybe we can, but either way, get minimum has to return -2.
And what
So
does get minimum do? Does it return? Are you updating the stack?
yeah, exactly. Get minimum. No, get minimum does get minimum does not pop off the minimum of the stack, right? Or
Yeah, it doesn't. It just gets the
it
minimum.
doesn't. Yeah, it
It
does
just
not.
tells
Okay,
you.
okay. So we sort of need a way to keep track of the minimum element of the stack. Um, so I'm gonna explore how far this gets me. What about uh, maybe a minimum variable, right? Global to the class or global to the solution object or global to the stack object. All right. And so now when we do -2, 0, you see our minimum is going to be equal to -2. Our minimum is going to still be equal to -2, right? Let me see if that continues to work. Okay. So now when we do, so for now, I think that works, right? Just having like a global minimum, like a constant variable. So let me see if that still works when you do push -3. We have -2, 0, -3, right? Now we see our minimum is going to be equal to -3. But then let's say we did pop -3. Then our stack becomes -2, 0. But then how do we get our new minimum, right? We would have no way of knowing our new minimum.
Yeah.
So what I'm noticing right now is that our minimum changes in relation to stack. So what I mean by that is, I imagine as like a sort of like time frame almost, where uh, you know, at the first push, we have at first push, uh, it's like each element in the stack almost has its own minimum that it can sort of keep track of, right? When you push -2, there's sort of a moment in time where minimum is equal to -2 and top is equal to -2. So what I'm thinking is the stack is not just a stack of current elements. The stack could also be a stack of minimum elements, right? So let's say you had another stack, maybe. Let's say you had another stack of minimum elements. Let's say another stack of min elements. When we do push -2, that was going to be equal to -2. When we do push of 0, when we do push of 0, that's still going to be -2, right? And when we pop 0, it's still going to be -2, right? So when we do -2, and when we push 0, it's still going to be -2. And when we push 3, it's going to be -3, right? So now we know, okay, when we pop -3, we can still get our get minimum because in our, let's say we call this like our min stack or whatever, or actually we couldn't call it min stack because that's like the name of the problem or the name of the class. Let's say whatever, minimums, right? Whenever we want to return our get minimums, we can just return the top of that, and that's O of 1 complexity, right? So we can sort of do actual data would be our stack, and minimums would be another stack, right? And every time we push data, so every time we push data, we push like an int to data, we push the minimum of that int or the top of minimums. Does that make sense? So when we tried to push, let's say we have 0.
Yeah, it does make
No,
sense.
we had -2, 0. So when we tried to push 3, okay, we're gonna update data 3 just like a regular stack. But then in our minimums, or -3, in our minimums, we're gonna push -3, right? So now theoretically, if we pop -3, okay, we can pop that, right? Don't waste space. We can pop this, don't waste space. But now we know what our last minimum was, and I think that could work for any sort of combination of push pop calls.
Okay, let's do a dry run with the input equals that one that you gave -2 0,
Yeah.
and when you dry run it, initialize all the variables that you're gonna be using, so I have understanding what you're gonna.
Yeah. To the class, we're probably just gonna be doing like maybe self dot data would be a stack. I'll just use like a list object to represent a stack for now. Maybe we can use a deck, but for now I'll just use a stack. Self dot minimums. Right. So those are the two I guess state that we're gonna keep track of.
Okay.
And they're at any given time they're both going to be equal. The length of both are going to be equal to each other.
Sure.
I guess that's invariant. I'm going to enforce.
Mm-hmm.
So yeah, in our input, these are like push operations, right?
Yeah. Let's say this is you're getting push.
Yeah. So when you push -2, we're going to, I guess, push -2 onto the stack, and we're going to push -2 on the stack because there's no other minimums in the stack. Okay. Go next up, -2. We're going to see it is 0. And here we're going to ask ourselves, okay, what is the minimum of -2 and 0? It's going to be -2. So theoretically, I'm not saying that our input says this, but theoretically, if you were to pop off 0 immediately, then we would still have our minimum right there, right? Yeah. But for now, let's keep going. -2, -2. So now when we want to push on -3 onto the stack, then we sort of have -3 right here.
Wait. Let's stop there. Quick. Okay, what do I do if I hit top? Click top.
Top?
Yeah, top. I call top.
So see.
Now the point, like we already pushed top, or before we push -3, we call top.
Yeah. Top would always return the top of the self.data stack.
Okay.
I guess I should have clarified that. Top, and pop. They get top of self.data.
Okay. Okay, let's push number 3.
Yeah. When we push -3, we push -3 onto the self.data, and then we ask ourselves, okay, what is the minimum of -2 and -3? It is -3. So now, even if we were to pop -3 off the stack, we still remember what the previous negative number was before we push -3 onto the stack, which is almost like it's like stepping back in time almost. Is like how I like to imagine it. And
okay,
I think that would just be like my approach.
Yeah.
These are the two states. These are two states that we're going to keep track of. And then in push, we are going to push both the self.data and self.minimums. And then the element that we're going to push onto self.minimums depends on which the lesser of the two, right? That's pretty obvious.
Let's implement.
Okay. So let's say self.minimums. We can start with empty stack. self.data. And just to clarify again, I think I asked this before, but for now there are no space constraints, right?
No space constraints.
Okay, that's good. So when we pushing, we don't have to worry about much. We can do self.data.push value, and we can also do self. And when we're pushing the minimums, like I said before, we're going to push the minimum of value and uh, the last element of minimums. But now, I'm quickly wondering, okay, what if minimums is empty? So we have to say if length of self.minimums is greater than 0, then we have that. Otherwise, we can just push push the current value. And that sort of models what happens with -2. Like when we push -2 on the stack, our thing was empty, so that was our first minimum. Okay. So now when we try to pop, again, we're assuming that pop is never going to be called on a non-empty min stack.
Mm-hmm.
So when we pop, we can we're eventually going to return self.data.pop. That's eventually where we're going to return. But before that, we have to make sure that our minimums are up to date. So we can sort of just do self.minimums.pop, if I'm not mistaken. Yeah, because let's say when you go back to our example, we have -2 and 0 and -2 and -2. When we popped off 0, we had to pop up the -2 that came with it.
Mm-hmm.
So yeah, I think that updates the minimum and it returns the popped element.
Sure.
Okay. Top, again, we're assuming it's never going to be called on a non-empty stack, so we can sort of just do self.data -1. And we don't have to update really the minimums because we're not like communicating the stack at all. So I think that should work.
Okay.
Now get minimum, right? That's like the whole reason I guess we're doing this problem. Get minimum. Get minimum. We're not going to pop anything off the stack, but what we sort of have to do is we're getting the latest minimum that we have. And the latest minimum that we've seen is going to be the last element of self.minimums, right? In the example that we gave, when we pushed -2, 0, -3, minimums was -2, 0, -3. And so the latest minimum that we saw was the last element of self.minimums. And so I think that's my final solution. There might be maybe a minor bug somewhere, maybe. But I think we're ready for a dry run.
Yeah, let's dry run the push right here.
I thought we were gonna dry run.
All right, let's just get it working. I think
Okay.
dry run is very specific to like some companies.
Oh, okay.
Like for Facebook, they'll make you dry run it hard, but I've never seen that at most other.
I see.
Like some companies, they just want you to get running code as fast as possible. Of course, dry running is good too, but I think let's let's
Oh, yeah.
focus on getting through to the next question.
Yep. The reason I kept saying push, but since it's actually a list under the hood, and not actual stack, it's like append. So append, and let me see if I say push anywhere else. What is the other error? Oh yeah. So here, minnow is not a local variable. Okay.
Let's get it. Nice
Okay.
work. We've got time for the next one. No, it's good job. One thing I like is that you're able to read the errors. Because one thing too, in some of the more practical jobs, when they let you actually run the code, you'll see people run the code and they will look at the error and still not know how to fix it, even though the error is kind of clear, and
Yeah.
that's the negative signal if you can't read the errors and understand what's erroring. But I think you're able to figure that out after we run it. You're able to figure that out most of the time. You're able to figure out
Yeah.
off by one, so that's good. Um, yeah, good intuition, able to figure it out. And let's move on to the next question. How do you feel?
Um, that was a good question. Easier than the last one, I think.
Yeah, still a medium, so good job. Okay, there's the final boss. If you get this,
Wait,
you
I have
know
to
you got
solve in
all.
less than 20 minutes because I have to leave.
Yeah, yeah. We'll solve
All right.
it. We don't even need to code it. Let's just cause I gotta work too. We don't even need to code it. Oh shit, gave you the wrong one. We don't really need to code it, but I want to see your intuition for how you'd solve this problem.
Okay. Okay. Do I need to know what a least recently used cache is for this problem?
Um, just I can read it out loud. Well, essentially, we want a data structure. We want a cache. Are you familiar with a cache? With what a cache is?
Yeah.
So we want a cache, right? That has some capacity. So pretend the
Hmm.
cache is like a dictionary
Okay.
that stores is a key value dictionary, key value store,
Got
right?
it.
So we it's a dictionary, but pretend that the dictionary has a capacity. So when the dictionary gets to larger than that capacity, we need to purge one of the keys.
Oh, the least recently used key.
Yeah. So we need to purge the key that doesn't really get used, or the one that
Okay.
hasn't been used. Right.
Okay. Um. Okay. Well, the problem says int key, so I guess a good question would have been, our key is always going to be integers, but the problem kind of says it for you.
Yeah.
And the values are always integers. Um. Let's see. Okay, so get is allowed to be called on like a non-existing key, right? That's
Yeah.
fine. Okay.
Yeah.
Okay. Um. Evict the least recently used key. Uh, so by least recently used, does that mean let's say I have a let's say my thing is like 1 1 2 2 3 3,
Yeah.
and let's say they were put in that order, right? So if they put one first, and they put two first, and they put three first,
Here,
right?
I'll give you a good example. Pretend our capacity is 3, right?
Mm-hmm.
Or capacity is 2. When
Yeah,
we put 0, 1, we put 0, 1 here, right? When we put 1, 0, we have 1, 0 here.
yeah.
When we put 2, what should we do? We don't want
So
to
our
go over our
capacity is two.
capacity.
Yeah, we should. We haven't used 0 or 1, but since we added 0 first, we should probably evict that first.
Okay.
So
What if
we
we
would sort of
That makes sense. What if we get 1? What should get 1 return? Or sorry, get 0 return.
zero is the key and one is the value, right?
Yeah.
Yeah. So get zero is going to return one, but it's also going to have a side effect where it, uh, I guess, brings zero to like most recently used, and now our one would become the least recently used. So now putting two would imply evicting one, and pushing two. When you put an element onto the LRU cache, does that become the most recently used element?
Yeah. It's a
Okay,
good
so
question.
by pushing it, it becomes most recently used. Okay,
Yeah.
okay. Um, just to start off the problem, I know probably for a fact we are going to need a hash map, just because it's like the nature of the problem requires key value, and hash map is sort of the only one that can sort of do that in in like constant time complexity.
Sure.
But we are probably going to need something else, right? Because we have the capacity and we have to evict uh, the least recently used key. I'm thinking for this like some sort of queuing behavior
Mm.
where we can almost have like a. I think the best way to explain this is just to sort of model the problem. So we have put the value doesn't really matter. The keys matter when we're like for the evicting behavior. So when we first push zero, it's going to be the least recently used. Then let me push one. So let's say front of Q is LRU, right? Least recently used.
Yeah.
So we have 0, and then we have 1. And then when we get 0, right? When we get 0, okay, we have to sort of, when we get 0, when we get 0, this sort of has to become 1, 0, right? And I know that getting an element from the front of a queue is from the front of a double-ended queue is constant
Mm-hmm.
time. Um, so I'm thinking, what if our hash map didn't store keys, but instead it is stored like are keys guaranteed to be unique?
Yeah.
Okay. So yeah, so we have 0, 1, get 0, 1, 0. Just sort of have to. We whenever we get something, we sort of have to find it in the queue. Like if we didn't have the hash map, right? We sort of have to find it in the queue.
Mm-hmm.
Like if we didn't have hash map, we would find 0 in the queue,
Mm.
take it off. Or actually, that's not even how a queue works. But yeah, it's like how would you take 0 from the queue and sort of make it into the front of the queue? Hmm. If well, maybe a queue isn't even right for this problem. Maybe I'm thinking about it wrong. But I feel like the evicting behavior like really makes me inclined towards the queue.
Mm-hmm.
So if we didn't have hash map, we would.
Makes sense. So you have some sort of ordering, right?
Yeah, yeah.
Most
But now the
recent to
problem,
least.
yeah, the problem that I'm wondering right now is get 0. We have to find 0 in the queue first and then do something with it. Uh,
And what's that thing we want to do with it? Throw it all the way to the back, you're saying?
yeah, when we find 0, we want to take it out and then put it at the back of our double-ended queue. Hmm. Well, maybe our hash map doesn't have to store data. Our hash map could instead store uh, maybe indices. Our hash map. Oh, okay. Our hash map could probably store indices. Like, what if our hash map stored like what is index associated with 1? Like, okay, it's still more sort of function as a queue, but let's say we have 0, 1, right? When you have 0, 1, we would ask, okay, what is the index of 0? The index of 0 is going to be 0, and the index of 1 is going to be 0.
It's gonna be one.
Or yeah, it's gonna be 1. And this could maybe be a tuple too, right? Because it also has to store the value.
Sure.
There could be value, what's it called, 0, value 1. And so now, and then we can sort of have another, I guess, list that sort of acts like a queue. So we'd have 0, 1. So if we had to sort of get 0, right? When we get 0, we would look at, okay, we would get 0 from the hash map. We would see, okay, 0 exists at position 0. So what I want to do is I want to sort of uh, get 0 from the list. Wait, this really reminds me of like this problem I did in DSA where I had like, but the thing is in DSA I had a sort of linked list, so the hash map could have stored a pointer to like existing elements, but here we don't really have that functionality.
Mm-hmm.
Uh, so I'm thinking we don't have pointers, but we do have
Okay,
indices.
so we have pointer to the zero, right? So when we
Yeah,
move the zero to the back, we're gonna update this to one. You're saying? Because now it's at the back.
yeah, but it's like let me go back to how it was.
Okay, go ahead.
So when we get 0, yeah, we want to sort of have this now, right? When we get 0, we want to have the following structure. We want to have 1, 0, right? So that we maintain this invariant where uh, the sort of the first element in our list or queue or array or whatever is the element that we want to evict if our capacity exceeds capacity, or
Yep.
if the number of elements exceeds capacity. But now the problem that I'm running into, which I don't really know how to properly, I guess, verbalize, is okay. When we get 0, we have to change this into like the length of the array. So let's say this is going to be 1, right? It's like,
Yeah.
oh wait, actually, I think I got it.
Okay.
So we can getting 0, we can pretty much uh, swap the swap 0 with the element next to it in the array. No, sorry. You're gonna swap 0 with the last element. Okay, but then you run into the problem. Okay, maybe, but then the last element isn't necessarily the last element is only one step away from 0. So it's like you sort of have like this cascading effect where you sort of have to like swap everything over, and that's not going to be O event. Like doing all those swappings is going to be O event,
Yeah, it's gonna be
and that's
open.
not. Yeah.
And you have to update everything in this map, right?
Yeah, exactly. Yeah. If we had like a linked list, like that would make this problem a lot more manageable because you would have pointers and you wouldn't really have to manage indices like that.
Yeah.
I'm just thinking, is there any data structure that's available in Python by default sort of has that functionality?
So could you explain the linked list approach?
Yeah, so with a linked list, I think the approach would be pretty simple. You sort of have the key, which would point to like the pointer in memory of node in the linked list,
So it's a
right?
W linked list or a linked list?
It would be a W linked list because you need to have access to both the front and the back.
Okay.
And then in the actual doubly linked list, the value of it would be like the value.
Sure.
And then okay, whenever we had to put, we would put it at the front of the linked list, and we would update our table. And then whenever we had to get, we would say get node in W linked list from hash table. Take it out because that's pretty easy to do in W linked list.
What do you do when you take it out?
You have to sort of like manage all the pointers so that are pointing to it and the
Yep.
pointers that it is pointing to.
Yep.
But that's sort of like already a solved problem.
What's
So
the time complexity?
it would be constant. It would be constant,
Okay.
which is way better than like managing indices in an array. And you would take that out, and you would sort of put it at the front. Right. So now you don't have to manage any indices, and that would work if we had a W linked list.
Yep.
But we don't.
Okay.
So
And putting it at the front, what is that?
O of 1. So put and get are both O of 1 in this
Okay.
case.
Yeah. Okay. Yeah, that's the solution. Yeah.
So it is,
But
but we don't have a W linked list. So what do we do?
You would have to implement it in the interview. Implement it, the whole thing.
Are you for real?
Yeah. This is a classic new grad question. You have to implement the W linked list operation. Let me see. It's not too much lines. I mean, it's a lot.
Are you? That's so much work.
It is a lot of
Can't
work,
be
but
true.
they love asking this at. I've got asked this at 6 different interviews. The same
Bro.
exact question. They ask you to implement it from scratch. It's pretty annoying. But yeah, you got the intuition.
Yeah, I knew you needed it because you can't just have an array because you like swapping all those indices would be mad
Yeah,
work.
exactly,
So you
exactly.
need pointers.
Okay, yeah, I think. Yeah, what I noticed good was yeah you had the intuition that we want to maintain some invariant where
Yeah,
it's
exactly.
there, we have some sort of ordering, so we know the least recently used. So when we pop the next least recently used, we know who the next up to evict is. But if that person ends up getting used, they should they should become the most recently used. So
Yeah,
we kind of
exactly.
had a
Yeah.
sorted array. So one way candidates solve this is using a array like you mentioned, but instead of
Yeah.
keeping track of the indices, what they'll literally just do is just sort the array, just keep or basically they'll they'll if something gets basically what you did, right? Where if something gets used, they move it to the front, and then they
Yeah, and then
shift
they
all
sort of
the
have
things.
to they just have to rearrange everything,
Yeah,
right?
but they don't like maintain the indices in the hash map as well. They do something else, but essentially that's an overend operation when you like push it to the front,
Do
right?
they ask this question and expect you to solve it in 20 minutes? Like
Not
implement?
20 minutes. They give you
Okay,
like 40 minutes, 45 minutes.
that's not that much. It is better, but like, who would know how to do you just know how to implement a W link list off the top of your head? I feel like just
I mean, you should have practiced it. I'm looking at the tags right now. It says 66 times asked at Amazon, 42 times asked at Meta, 16 times asked at Microsoft, and this is the last 3 months. Like this is just
wow.
like it's just you should be able to implement a W link list in like 20 minutes.
Okay.
But it's just practice, right? It's yeah, it sounds dumb, but it's asked like crazy. I've got asked this like 6 different times in different interviews, so it's kind of just muscle memory. This question, but yeah,
It's kind of a terrible question. I'm not gonna lie. Like it's like thinking about it is like 10%, and the actual other 90% is like
yeah. No. Good thing you're using Python. In one interview, they forced me to do this in Java, and I was like, bruh. But yeah, okay. Have fun at school, man. Good luck on your interviews. Let me keep us updated on how it goes. I hope you get it, man. Hope
wait,
you
wait,
get it.
wait. Yeah, yeah.
You got
Wait,
questions or no? Before
yes.
we end off.
After you stop the video.
Yeah, yeah. Okay. All right, I'll stop it now.